So the presentation I'm giving today is hopefully, it's a bit echoey. Is that normal? Yeah, okay. Right, so the trouble with triples. So it's based around my recent experiences in Neo4j professional services, working at trying to bring RDF data into Neo4j, into a labeled property graph. So just of what we're gonna cover. So I'm Stuart Green. I'm one of the consulting engineers at Neo4j. I've been working with a couple of colleagues, Moritz Wegener and Maxi, who's actually here today as well. And we've been working on one particular custom project looking at RDF and how we can bring that into Neo4j. So we're just going to go through some sort of basics of RDF and what that means, the various challenges we've had from our customers, and then ultimately some sort of concluding remarks of our experiences in that field. So to avoid confusion, we're not talking about tribbles in this case. So I know there's going to be some Star Trek geeks here, but you know, if you can recall, going back to the 60s or 70s, some of you might have been there. There was a famous episode of Star Trek involving these things called tribbles. But we're not here to talk about them. But the thing to remember about tribbles is tendency to multiply rapidly, which can lead to significant problems. Okay. We're also not talking about Belgian triples either. They're another thing that can cause problems, is Belgian triples. But you can see, you know, they're top fermented, then they pair well with cheese and seafood. But we've probably all had enough of those over our time anyway. So just to be clear, we're ruling those out as well. But what we are here to talk about is triples from the resource description framework. So these are our semantic triples. So they're an atomic data entity. They tend to be highly unstructured, and they have a tendency to multiply rapidly and cause significant problems, just as the triples. So what we have, just to sort of familiarize yourself with the terminology, is we have these RDF triples, which consist of a subject, a predicate, and an object. The subject is the thing that we want to describe, and you know, it's some sort of statement about it. The predicate is a property or a relationship which is associated with that thing, and then the object is the resource or the value which is attributed to that thing. So, subject, predicate, object, things you just have to remember. Okay, so the way these are usually expressed is in the form of URIs. So in this case, we've got our drug, which is aspirin, and it can be expressed as this URI, where we have the concept, which is drug, and something which is aspirin. We've got, in this case, our concept in and around treatment, and our concept, which is a symptom, and this is headache. So we could represent aspirin treating headache, basically using these URIs to create our subject, our predicate, and our object. And then we can also represent literal values. So in this case, we take the same example of aspirin. We've now got some entity, or not entity, something in and around representing dosage. And in this case, we've got a literal value. So some sort of text or number, which in this case, we're going to say is 300 milligrams. So we can represent other entities if we go back. So in this case, we have our entity or our thing, which is headache. And on this one, we've got our literal value, which is a number or some string representation. So, you know, very basic ways of representing data. Okay, and then what we can do is build those triples up into a triple store. And in that case, a triple store is just a big table with subject, predicate, object as headers, and then we can search this table using, you know, traditional indexing and things like that to find all these different things within our table. And we can build this up to create a knowledge graph. If we got tens, hundreds, thousands, millions, billions of these triples, and we can build a very big triple store. So there's a number of triple store providers out there, and this was taken from, was it DB Models or something like that, just showing who the sort of top providers are, people like MarkLogic, GraphDB, Amazon Neptune. Some of them are multi-model, so they'll do RDF triple stores, they'll also do SQL databases, and some of them are specific RDF. But we've got a range of different popular systems there which can provide triple stores. So, RDF and LPG. So we've got our resource description framework. How does that relate to labeled property graphs? So I'm a chemist in my ancient background. So I don't know, I'm sure some of you also have done sort of chemical training, and you can remember these, these orbit molecular modeling kits. So if we consider this on the left here to be our triple store, so each one of these things at the end you could see as a sort of a different resource or something like that, and it's linked. This is our predicate and a direction with a little yellow marker on, and that's linked to that blue thing. Now, in a triple store, yeah, we've just got this big pile of list of triples, but when we actually turn it into a labeled property graph where we're actually joining the things together, this is how I see it. So the labeled property graph is turned effectively a series of strings or a series of connections. We've realized that into some sort of structure when we've moved it into the labeled property graph. That's how I perceive it anyway. So this is just some commentary. I'm not taking any credit from this, but this is from a guy called Orla Lassia. He's a Finnish computer scientist. I think he's head of technology, or one of the heads of technology within AWS in around their Neptune piece. And this is his view on RDF and what it's good for. So you've got good features, so graph merging, reasoning, federated queries, and missing features. So those are his views in and around RDF. And this was published, I think, a couple of years ago. And these are his views around labeled property graphs. And you can see all he's done, not me, it's just the missing features from the LPG world and the missing features and the good features from the labeled property graph world are interchangeable. So that's what we're trying to do. So we're trying to get the things which hopefully you guys have stored in your RDF world, we're trying to bring those into the labeled property graph world so we can bring on these good features, which is all about path discovery, composable queries, recursive queries, and all the analytics capability that we can do within the labeled property graph world. Okay, so how are we going to migrate that data between the systems? Now, traditionally, we've had a couple of tools out there from Neo4j, and these are sort of community-supported tools. One of them is Neo-Semantics, and that's available as a plugin into Neo4j infrastructure, but it's not available on our Aurora platform. We don't support plugins within our Aurora platform. So we've had to rule that out because the work we were doing was ultimately going to bring the data into Aurora, and we looked at using RDFLib with a Neo4j backend as an alternative to Neo-Semantics. So RDFLib is a Python library. So we now come on to the challenge which was set to us by our customer as to how are we going to bring this large amount of data. Can I just get some water? So how are we going to bring our RDF data into our labeled property graph? Now, the customer TTL data that we had, so it was in turtle files, which is a common format for using, for running with RDF data. We were given just over 10,000 files and 1.5 terabytes of data, and we're expected to bring that into our Neo4j graph. So that was our first challenge. Now, the first trouble we hit with that is just the sheer size and scale of that amount of data. If we use RDFLib, we've got a problem because as it operates, it performs merge and set operations within the database. And for every merge operation, you have to do a lookup in an index and then include and merge the data into the database. Now, that's fine if you've got, hundreds of thousands of entries, millions of entries maybe, but when you get into the billions of entries, it slows things down. So it doesn't work doing that because the nature of RDF data is that it's inherently unordered. The order doesn't make any difference. So we look to change that and use a sequential load and bring that data into Neo4j and try and speed things up. The problem is with when doing this merge and set operation, we can't parallelize the import. It tends to lead to things such as node locking within the database, and that can slow things down even more. So we can't parallelize and have multiple files updating into Neo4j at once. We can only do one file at a time, and that's obviously a massive problem. If you've got 10,000 RDF files, you want to load it to Neo4j. So our first estimation of trying to import this data, it was going to take us more than 100 days just to import that data, which is obviously not something you want to hear. So we looked at an alternative approach and started to modify the RDFLib library itself. And we brought in an intermediate store to actually store all the node properties and all the relationships before we push the data into Neo4j. So we're basically enabling our ordering of the data. And then in that process, we can use a create statement in Cypher to update the data in the database and remove that need to look up every single time. So that can speed things up. So we were able to do that, and that helped us improve things from being 100 days down to probably something in the order of about 10 days. So, trouble two. The other problem with RDF is multi-valued properties. For every single triple that we have there, we don't know until we've run through the whole data set how many dosage properties that we have there. So we don't know whether we can treat this dosage as a single property or as a list. So if we're dealing with multi-valued properties, we have to treat it as a list. And that causes a number of problems because if we've always got that list, every single query we do, we've got to do some sort of list manipulation whilst we're performing that query, which isn't particularly performant. And in Neo4j, arrays of strings are not indexable. So we can't include any of the indexing there. So we need to do something with those multi-valued properties. So once again, what we decided to do is build a transformation framework post our ingestion of the data into Neo4j and transform it selectively based on the data and what we knew about the data into either a collection of nodes or a single value or a concatenation of strings or some sort of aggregation that we would perform on that list. So there's a lot of post-processing going on in this. And what that means is, if you say we take aspirin, or this simple example of aspirin, which had this dosage, what it results in is us creating a number of additional nodes, each representing this dosage value. So we're promoting those values for that particular drug. And then if we look at a slightly more complicated example of some of the data which we imported, which was around an adverse event, you can see that we've got some nodes which are connected to this node which has all these properties in the middle. And you can see that they are all currently list values. So we would apply our transformation to that. And that would result in us adding further nodes into the graph, which represented some of these things which were in this list. So we're doing this post-transformation on there. So that's trouble 2, and then we come to trouble 3, which we came across was lumpy data. Now, this is something we tried to batch the data in RDFLib, and that allows you to do batching, but we found that we had such a non-uniform distribution of data in there that we've got some of these literal objects in there, which some of them might only be 1 byte. They might be a Y or an N for yes and no, up to massive chunks of descriptive text, which could be 10 to 100 megabytes long. And that would just throw out any batching that we could try and do. So we introduced actually a dynamic batching step into the RDFLib so we could load these far more effectively. Okay, so the outcome from that, which was back in December last year, that we were able to basically import this 1.5 terabytes of RDF data, and you can see that we were able to build 4.6 billion relationships, which turned into 6.4 billion relationships when we expanded everything out. So we were able to transform, this 1.5 terabyte set of RDF data into a Neo4j database. But yeah, it's now getting quite sizable because we're at the sort of billion node, multi-billion relationship level. Okay, so that was challenge 1. So yeah, we can import the data, but we've had to modify some of our tooling, which in this case was RDFLib, to try and bring it in a faster way. So challenge 2, triple store changed a bit because the customer asked us that, okay, well, we want to actually now understand for every single, say, literal value we have in there, it's all come from some particular data source. So it has some provenance, and that provenance is being described by RDF star within the RDF world. And this provenance information, as you can see on this example here, so we've got a drug here, it's got some particular warning associated with it, and we've got a relationship here which is representing the source from which that information has come from. So within database A, it references cardiotoxicity for this methadone, and also in database B, but the provenance could change. There could be different things coming from different sources, and that's what we wanted to capture as we import the data. So just a little piece in and around RDF start, what it looks like when you actually see the triples. You have this sort of additional notation in there, which is representing that for aspirin in this case, that the dosage of 300 milligrams is delivered via a particular tablet, and that's using RDF star to describe that. So we're trying to describe, in this case, a relationship property using RDF star. And fortunately or unfortunately, we couldn't do this with RDFLib or even near semantics. So what we looked at is a completely alternative approach to now bringing the data into Neo4j. So we looked at actually using a triple store itself to take the customer data and transform it more into a form that we could actually use to then import into Neo4j. So we're looking to transform the RDF data into CSV and then directly import that into Neo4j. So we chose to use, in this case, Apache Jena because it was available to us, it's well understood, it's free, which is the main thing as well, and it's performant enough. It might not perform as well as some of the triple stores out there. I'm sure many of the commercial ones are much, much quicker, but this gave us a platform that we could write Sparkle queries on and get it to generate the CSV that we needed to bring into Neo4j. So our transformation recipe then sort of changes that what we want to do, if we're going to include this relationship information about provenance, we need to promote all the literal values. So if we look at our dosage of 300 milligrams, if that's for a particular tablet form, we have to turn that 300 milligrams into a node in its own right, so we can write a relationship property to it. So all the literal values within the RDF graph all have to be promoted. And that involves creating basically a new object, a new unique object in our triple store to represent that promoted literal. And then you then have to create a new predicate to that object as well. So we wrote Sparkle queries which would do all of that. And then, so this is just an example of that literal promotion. So we would have that literal, which is aspirin, has a dosage of 300 milligrams. We have to create something in a new namespace, which is our dosage of 300 milligrams. And that has an RDF type and an RDF value of 300 milligrams. And then we also have to create a new predicate in the triple store as well, which is linking aspirin via this new has dosage relationship to our subject back there, our object, which is back there, which represents the dosage of 300 milligrams. So we have to do a lot of processing on the data. And yeah, that's the result of it. We would have previously had this dosage as a list, and in this case, this transformation results in this multi-dosage, these additional dosage nodes and the additional has dosage relationships. So our transformation recipe becomes promote all the literal nodes, create new objects, create new predicates, interpret then the RDF star, which is then associated with that relationship property, and then convert that all to CSV, and then we can import that into Neo4j. So we wound up with this workflow that we could apply to, does this give us, yeah. So this workflow that we use then to transform, once again, the 10,000 or so RDF files, basically taking the provenance information that they have there, and then the description, the actual data itself, which is the concept, and running it through a series of queries. And you can see the queries Q1, Q2, Q3. So these first ones are basically regenerating the provenance, doing the literal promotion as in Q3, creating new predicates, and manipulating this data through a series of triple stores to ultimately, when we can extract the nodes, create the provenance relationships, create anonymous relationships, because there's relationships in the data as well which don't have any provenance information. And then for the promoted nodes, create those new nodes and bring them all together and import them into Neo4j in one step. So, we'd have done this for 10,000 odd files, and then ultimately we'll get to the stage where we will bring them all together in one Neo4j admin import, where we've got all these CSV files, we bring them all together and generate the Neo4j database. Now, this has one advantage over, or the main advantage of this over sort of other approaches is all of these steps and queries can actually be parallelized. So if we can throw enough compute at this and enough disk and things like that, we could potentially do this all at once to bring it all together for that final step and import it into Neo4j. So outcome 2 of that. So this is a system where we had 7 billion triples. We resulted in 52 million nodes with 4.6 billion relationships. And that brought us one graph that we were able to bring together in April 2025. We've since done other ones which have been slightly bigger, in around the 9.3 billion triples. We've been able to bring all of those into Neo4j. But it still takes some time to process, to do all this processing. Okay, challenge 3 is another one where the customer provided us with just with one file, but it had 17 million triples in. But unfortunately, the trouble with this one is they didn't give us any data source description. All we had was just an RDF file. We didn't understand the concepts within it. We just had to glean that information by doing some analysis, some Sparkle analysis on the RDF. And what has that has now led us to actually develop basically a universal sort of RDF import workflow that we could use where we don't have that data source information. But it involves a few more sort of queries. So we have to, as you can see here, we've got a series of queries that we need to run against that RDF file. So first of all, we need to find out all the concepts or canonical types, all the unique ones which are in that file. Then we need to define all the unique predicates which are then associated with it. And then we can also find all the singletons. So there was a request from the customer that they didn't want, where there was only a single property and it wasn't a multi-valued property, could we just have that as a node property rather than that as a value of a node where we'd expanded everything out. So we had to do we developed a way of doing some sort of singleton analysis and identifying all those singletons such that they could come in as single properties. And then obviously we've still got to do these new predicates, do the literal promotion to avoid the multi-valued properties, and then through those same sort of queries again, we can create our raw nodes, our property nodes, our relationships, all through Sparkle queries, get the CSV that we need that we're then going to import into Neo4j. So those are the challenges we've had. So we've gone from, RDFLib and Neo-semantics, which I would say are probably good for RDF libraries or RDF systems where you may have, million, maybe tens of millions of triples, to a system now that we're doing things with maybe 9, 10 billion triples. It's still taking some time, but what we need to do is really, you really need to consider your data before, committing into this because of the sheer time involved in it. So the key thing is obviously, if you can have a data description so we know what the canonical types are, what the predicates are, so we can actually do the analysis on those. So have a clear data description. Also, please, 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 think about the data you actually need in Neo4j. You may have everything in your triple store, but do you actually need all of that data in Neo4j? Do you need huge, great text, chunks of text? Is that something you're actually going to search in Neo4j? So give some thought about data selection before you embark on this sort of process, because that's only going to slow things down if you're trying to bring all this data over. So think about what you can select. Particularly if you're doing a pilot, try and select a good set of data. Like I say, don't just go, well, we've got the triple store. We want to import absolutely everything from the triple store. Also, the thing we did discover as soon as we start bringing data into Neo4j, we can do a bit more analytics on it, we start to see duplication of data. And that's things, do have unique URIs, but if you're, say, looking at diseases or something like that, you'll find the common sort of data mistakes, capitalization and non-capitalization, commas missing, full stops missing, and all of those changing the data slightly or resulting in us creating additional nodes which may not be needed. So, there's data duplication, but we can now see it in Neo4j, so we may now need to look at doing some sort of level of entity resolution to bring the number and the type of data down to sort of the unique things we actually need and not unnecessary duplicates. And don't skimp on resources. We've developed this sort of solution now where we think we can throw a lot of resources at it in terms of compute and disk I/O to parallelize this, to bring the data in as quickly as possible. So don't skimp on resources. Ensure you've got big enough compute and I/O powers to actually do this. So finally, just a bit of word about professional services within Neo4j. We've got a sort of graph methodology, and we're here to help you plan and develop your Neo4j solutions from planning, design, develop, deploying, and expand. So we can go from the proof of value, the proof of concept, all the way to production systems. There's a group of us spread across Europe and in the US as well, and we tend to work around the whole of the Neo4j ecosystem. Obviously, our Our strong elements are going to be, in and around the Neo4j piece, in and around Cypher and APOC and the graph analytics space. But we get heavily involved, as you've seen, with doing the whole data import and bringing the data into Neo4j as well. So that's it from me. So if you want to get in touch with professional services, EMAPO at neo4j.com. And as I've said, I've been Stuart Green at Neo4j. Thank you.
Thank you, Stuart.